the webcam here. There we go. Okay. It's 8:01. I will go ahead and start with the spiel. Boom. Okay. So, well, I'm going to talk about databases today. And more specifically, I'm going to talk about relational databases a lot because I think, to the layman, a database is generally like anywhere there's a bunch of information, right? To IT people, generally a database, we would call that structured data. And then most of the time, when we say database, we're talking about relational databases. But I'll talk about both a little bit just so that you have an understanding. My name is Ryan. I've been a system administrator or a cybersecurity expert or many other hats in the IT field for about 25 years. I am a self-taught person. I do a lot of Udemy courses rather than go to college or anything like that, right? So I sort of skipped out on all that stuff. Went straight into the workforce. Pretty good at IT stuff, though. Yeah. Boop. Okay, so if you have questions, just ask them in the chat. I have it over to the left, right there ish. So I will see them, or if someone wants to answer, feel free. Just so you know, the presentation is being recorded, and you can find the past sessions on YouTube. Yeah. If you're here, you probably followed a link that I posted that has that playlist, so I'm not going to post it again right now. But if you do need the link, post in the chat. Okay. All right. So straight into relational database. I like to start with pictures that are dumb, right? So in this case, it's a cat, weird cat face. I don't know where my cats are, which is weird. They're usually right around me, but not today. Okay. So as I said, relational databases, by far the most common. If you say database to an IT person, they're probably going to think to themselves a relational database. A little history before the database always existed, right? But in the 1970s, IBM already had the market cornered with IMS. It was their version of the database. There was a man by the name of E.F. Codd, I believe. I don't keep notes. This is from my brain. So, E.F. Codd, uh, he works for IBM. He invents the relational database. IBM already has the market, so they're not interested in it. So he leaves. He goes to what is now called Oracle, and Oracle basically takes over the entire database market, right? There's different types of database, right? I already said relational. There's object databases. If you're doing like object-oriented programming, we're not going to talk about it because it's not important. There's graph databases. Again, not going to talk about, not that important. Key value store databases. Now these are somewhat important, and so I'll talk a little bit about them. But then relational database, understanding relational database is almost like a key concept to understanding computers in general, right? So if you start understanding how databases function, you'll find that generally programs function very similarly. So it's a pretty important, data structures are a pretty important thing to understand, even for just basic computing. once you understand how computers work, whether you're doing simple tasks or complex tasks, uh, it becomes a lot easier. So there's these things out there called data scientists. There's a lot of jobs in databases. So you have your database administrator, right? And those people tend to just keep the database running, whatever database software they're running. Maybe it's Oracle, maybe it's MySQL, Microsoft SQL, PostgreSQL, IBM Database 2. There's a bunch of them out there. Most database administrators know one or two of them. Some of them know more, some know less, and their job is just to keep the database running and maybe sometime run some queries and tune it. You also have data architects, information scientists, things like that. People who maybe aren't as knowledgeable about the specifics of the database program, but understand how data works and how it is linked together. Data scientists are good at being like, okay, well, I understand that a first name plus a last name describes a person, or I understand that every person has a unique social security number, and therefore I will create the data like this, right? Programmers generally, if if you're a good programmer, you generally know SQL. It's pretty important just because the fact that programmers that use SQL and put their data into a database, a lot of your code almost is written for you, right? Like, for instance, let's say you have a program and it stores names, right? And then as part of that program, of course, they can sort by name, they can sort by zip code, they can sort by this, sort by that. Uh, if you were a programmer, you would have to write a function that's like, oh, take all this data, sort it by zip code, you know, that that is probably a day's work, couple days work, maybe, or you could just let SQL take care of it. And I'll talk a little bit about that, like have the database take care of it, which is basically you go to the database and you say, "Hey, I would like this data, please sort it by zip code." And the database already knows how to do that and how to do that very quickly. So at that point, your programmer isn't sitting there writing code to like sort things, right? Someone already's done that work for you. So there's people like data stewards who basically know how to use a database and know how to take things in and out of a database. Most of the people I know or I run into who know databases, what actually happened is they're not in IT at all, right? They had a job somewhere, and that job had some sort of program that stored data. And they found the program didn't really meet the needs at some point, and somebody was like, "Okay, how's this program work?" And they realized, "Oh, there's a database behind this." And then, at some point, somebody gets sort of curious and it's like, "Well, can I just connect directly to the database rather than going through my program?" And all of a sudden their business processes start changing. Instead of going into the program and being like, "Hey, I need all the people whose last names start with a V," right? Maybe the program doesn't have that ability, right? It's something that they specifically need. And all of a sudden they're like, "Well, I could just write a database call that does that rather than using my program." So all of a sudden your people who are sitting behind keyboards and used to be going into like some sort of program are now connecting up to a database and running queries. They're getting smarter, right? That most of the people I know who know SQL or know databases, generally somewhere someone in their business was like, "We need something more," and they learned how to use the database that they already had. So yeah, and there's a lot of databases out there: Oracle, MySQL, Microsoft SQL, Postgres, IBM DB2. There's many more. The thing that is probably most important is they have tiny differences that are not important. You can know by knowing one of them, you know all of them except for the caveats. So you don't have to like know MySQL, up and down, back and forth. You just have to know one of them. And that's about it. And it's not as hard as you might think. So, okay, that was the beginning. Uh, uh, my friend E.F. Codd from IBM. Uh, anyways, so next slide. Rows and columns. So to understand databases, I find it simplest to think of a spreadsheet. So at the bottom here, I have a spreadsheet, right? We have customer name, customer phone, street address, city, state, zip code. Uh, you know, this is an order spreadsheet. So what they ordered, how many, the unit price, and the total, right? You see these all the time if you work in a corporate environment, freaking spreadsheets. No one wants to deal with them. But it's a good starting point to talk about database because so as we get more orders, we grow vertically, right? Up and down, where we'll add, before Bob Smith, there was just Ryan and John. And then when Bob Smith made an order, we added another row. We're growing vertically. Um, and those are new orders. If we want information to describe the specific orders, we grow horizontally, right? Let's say, for instance, um, originally customer phone did not exist in this, and so somebody added that column to the spreadsheet, and so the spreadsheet grows, you know, horizontally, right? So that is called a field. A field is one of these columns. Like state is a field of the data. What state? I see some inconsistencies in this field. Look at the top one. It says Ohio. Look at the two underneath it. They have the abbreviations, right? Not important right now. But anyways, so a field, this is a descriptor of the data. So, and one important thing is that if you're doing this, if you're putting all the data in one big spreadsheet, and every time you need another something that describes the data better, you add another column, all of a sudden you're getting very horizontal, right? Uh, if I look at this, let's say, one of the things that's missing is the date of the order, right? So someone's like, oh, well, we need the date of the order. And then the next person has a requirement. They say, well, we need the date at which we fulfilled the order. And so they add, another column. And then someone comes up and they're like, oh, well, we also need their email address. So they add another column. And different sets of this information is relevant to different people, right? If you're in the delivery portion of the company, you don't care about the customer's email address. You just care about the label that's on it and what they ordered, and boom, right? If you happen to be the salesperson or the marketing person, you don't care about their address at all, right? You're not going to their house, but you might be interested in the customer's phone number to make cold calls or just ask them if they got the order or something like that, right? So different people have different requirements of the information, and people always want more, so it will keep like getting longer and longer, right? If Ryan makes another order after this, so there is a column number 5. Let's say he orders 17 more MacBook Pro 15s. All of a sudden, we have data that's duplicated. We have Ryan listed in this row number 2, and we have Ryan listed in row number 5. But Ryan's information is going to be the same, right? It's not like he moved or anything. The street address is going to be the same. City's going to be the same. State's going to be the same. Zip code's going to be the same. The only thing that's going to be different is the item quantity, unit price, and total. And the total doesn't is just calculated based on the quantity times the unit price. So that doesn't even need to be there in the first place. But it's there because someone needs it for the spreadsheet, right? Somebody somewhere. So it doesn't scale well because there's no data deduplication, right? We're just adding more and more vertically, and as we grow and need to describe our data, we grow more and more horizontally. People in IT have dealt with this for years. The spreadsheets that are just too much, right? So, and then from just a computer perspective, or just thinking about our eyes, right? Like, let's say that we're not tool assisted or computer assisted. If I had to go through this and search for Ryan, um, I would basically have to go through all the data. Is Ryan on 2? Is Ryan on 3? Is Ryan on 4? Is Ryan on 5? Um, Not awful, but computers generally work in very inefficient manners if you don't tell them to work in efficient manners. So you don't want your computer doing that, right? You don't want your computer to just like searching everything constantly. Like, is Ryan here? Is Ryan here? Is Ryan here? Right? Okay. And then, of course, if I need to update something, like what if Ryan's address changed? um, we would have to go through every row that Ryan's address is in and change it. So row number 2 and then row number 5 if I had data there, right? That's extra work. Why can't we just update it in one more place, in just one place, right? And that's where relational databases sort of come to play. So let's go to more of what you would think of as a database, a relational database, which is more instead of lots of or one big spreadsheet, we have lots of little spreadsheets, and then we have things that link them. So, for instance, let's look at our order table here. We no longer have customer information here. We just have a customer number. And then this other table has our customers, right? We have Ryan here, he's customer number 2. We have John Bonham, customer number 3. And we have Bob Smith, customer number 4. And at that point, if we need to update any addresses for Ryan for these orders, we just update it right here, and both of these will by virtue be updated. So at that point, the problem is, of course, if you're looking at this, you're like, oh man, but I don't know who customer number 2 is. I don't know who customer number 3 is. I'm not doing this like visual thing, right? It's hard. So, generally what the computer does is if I'm like, hey, give me all the orders that Ryan made, the computer queries first the customers table to get the ID that is Ryan's ID, and then it queries the order table for any orders where customer equals Ryan's ID, which happens to be 2. And we're going to talk about that a little bit. Okay, but for that, database schema. So databases are a set of tables, right? So if we go back here, we have orders and we have customers. So another thing we might want is this stuff here. Anyone who's ever worked in, a fulfillment center or a lot of factories, they know like part number, like we inventory based on part numbers, and those part numbers might be a whole nother table where instead of an item here, it's just a part number, and then we would have another table that's just part number 1, MacBook Pro 15. Part number 2, MacBook Pro 17. Part number 3, IBM Lenovo 15. Part number 4, IBM Lenovo 17, blah, blah, blah. So all of a sudden, this order table, you just have customer number and item number. And then I would put the price in the part area probably. So the part database would have part number, what the part description, and the price. So all of a sudden, this table gets even smaller because I only need the quantity that they ordered, because the item and the price are going to be in a totally different table. So at that point, right, I just need item number, quantity. Obviously, I don't need total in this column, right? I'm calculating it anyways. So boom. All right. So this is more like that's a very small schema, right? Now, most of the time things are a lot bigger, right? If you think about a phone book or something, right? Uh, a name and then an address and then a phone number. In this case, we have uh, let's see. Oh, this is a some sort of order database. Yeah. Okay. So over here we have order details. Actually, we'll start over here. Orders, right? And we see there's an order number and there's a customer number. So right, customer number, and then we have all the information here that describes the customer, and we have a table over here that describes payments, so that we know whether they paid. And then so we have the order number over here, and that links to the order details, as in like what did they order. And then over here we have the products, and that links over to product lines. If we look over here in customers, we have customer number, and then why do we have employee number? Oh, sales rep employee number right here, right? So whoever was the sales rep gotta pay out our commission, right? So that links to your employee table. You have an employee number, and that links to the offices because there's an office code, right? So rather than having a bunch of employees with the same address, the old way, instead, you just put an office code in there, and then you have a table that has those offices in it, right? Wow, gets visually it's complex, but it is the easiest way to understand it, in my opinion, right? So, okay, so each column also though has a defined data type. So, for instance, your customer number, well, that's a number. It's going to be an integer. Why do I say integer and not number? Well, a number, sometimes maybe it's an imaginary number or a negative number. No. In this case, it's a customer number. We'll say it is an integer. And normally you actually uh, specify when you're creating the database, you specify how big that number could possibly be. Normally, people always aim too low for this, because what'll end up happening is you're like, yeah, we'll never have 32,000 customers, and then your company blows up and is amazing, and everyone wants your products, and you're like, oh crap, we said we'd only have 32,000 customers. We're gonna have to alter our database a little bit, which is easy enough. So each of these, so we have numbers. Okay, so we have names. Those are strings, or just you know in programming and in IT, we call those strings because they're just a string of letters. Ryan, RYAN, that's a string. Phone number, there's a few ways to store phone numbers. I would probably store them as a string. Until we get down to zip code, I would obviously put zip code in as a number. City and state, obviously they have to be strings. Country, um, we know it's a string. Sales rep employee number, obviously a number. Credit limit, gonna be a number. Yeah. Uh, the only other thing, and then date is another important one. So date times, computers and databases are also very good at managing dates and times. So, for instance, rather than writing a program or code that says, give me the orders for the last week, you would write a database call that says like, hey, select the orders from now minus 7 days, and your database will magically be like, oh, here again, someone has done the work for you. So your programmer isn't sitting there writing that routine. Some database nerd who wrote your database program wrote that routine for you. You don't have to do it. Great. Okay, so an ID in a column can just be a pointer to another table. This is called a foreign key. So, for instance, the sales rep employee number right here links to employees. So if, I am sales rep employee number 6, and then over here, employee number 6 is, you know, Doe Ryan, I'm extension 420, here's my office code, et cetera, et cetera. So an ID in a column can be just a pointer to another table. That is why it's called a relational, because these data types or these fields relate to each other. So and then a foreign key will commonly point to a primary key. And what I mean by that is sales rep employee number is a foreign key in the customer table, but in the employees number or in the employees table, it is a primary key. Um, your social security number is a good example of a primary key because it is unique. No one else, hopefully, has the same social security number as you. You want your primary keys to be unique because it allows you to access the data as quickly as possible. For if we go back here and we're like, hey, uh, show me all the customers customer number who are customer number 2, that's very easy to figure out very quickly, right? Well, there and there, boom. It's an integer, it's quick. If I wanted to remove one of these, let's say it's very easy. I just say delete from customers where customer ID equals 2. There's no confusion, no risk of accidentally deleting. Assuming customer number 2, Ryan, is the one I want to get rid of, if I say delete customer number 2, it will delete the right thing. If I say delete Ryan, well, maybe there's another one down there and they accidentally get deleted. But customer number 2, very specific, and it should always be unique. And you say, well, that's a weird sort of use case. No, in databases, there's always an instance where you have to go and like take something out. It can get a little bit hairy if there's like relations going on and you have to sort of like unwind, like, oh, well, uh, I want to delete customer number 2, which is Ryan, but to do that, he's got active orders, so I can't just delete it because he's customer number 2. So then you go into the orders table and you delete anything that Ryan ordered that has customer number 2, right? And then you delete customers. Very confusing, right? You don't have to worry about it. Okay, but the important part is your primary key, if you're designing a database, should always be unique. The layout of a table and columns that are used to describe data, that's called a schema. Weirdly enough, I've heard people who use Microsoft SQL use that word differently. I think, though, outside of that, everyone calls this picture to the right, they call that a database schema. Boom. All right, so we're going to talk about SQL. Okay, so SQL is the language that you use whether you're doing it manually or as part of a program to interact with the data, right? Some people say SQL, some people say SQL. The language has some verbs that are always at the beginning. So so it's used for both the creation of databases and getting data out. So you'll see to my left, there's a create, or not my left, your left, create table persons, right? This is SQL code, create table persons, with what I'm creating inside that table. That is SQL code. And I know it looks complex, but you're not, if you end up having to interact with databases, you're not going to be the one creating tables, right? And so over here, there's show tables, and that's easy enough. It shows you the tables that are in the database you're using, right? There's also select, which is a read operation. There's insert, which is adding another row, and there's modify, which is update the data. And we're going to talk about that. Yeah, we'll talk about. Surprised I did. Yeah, insert first. Okay. Uh, insert is used to add a row, right? Uh, Actually, hold on. I have. Oop, here we go. Second. So have this, and then also, actually, before I do that, let me get rid of this stuff. There we go. Okay. This. All right. So you'll remember last month, maybe you will, maybe you won't. I went into the cloud and I showed how you could create computers and create databases. So what I've done, I thought I only did one. I was gonna delete one of them, but I apparently forgot. Well, give me a second. Let me delete this. Wait, delete me. It's just as easy to delete things in AWS as it is to create them sometimes. All right, so I have my database here, right? So what I did is I just went into AWS yesterday and I created a database. It's that easy, right? I think I did it as Aura, I think I dev, and gave it a password and made it tiny. And then I hit create. That's what I did yesterday. We're not going to create another one since I already have one. So we have my little database instance that's sitting out there that I created in Amazon. And then I have a machine that is I am no longer connected to it. Now, can I remember the password I set for it? Yeah. Show databases. Yes. All right. So that was pretty easy. Created a database in Amazon Web Services and brought it up. All right. So let's go back over here to my this. All right. So we have our create table and our show table. So I will go ahead and create a table real quick. Well, first I have to create a database. So let's create database, and we'll just call it business, right? So show database is. There we go. So we have it, right? And so at that point, I want to use that one. So we'll just use it. Oh, one thing about SQL I should have probably mentioned, everything ends in a semicolon. Semicolon basically is SQL's way of saying this is the end of the operation I want you to do, right? Anyways, so also we'll create this table. I've already got it typed out. Boom, easy query. Okay, if I did something wrong, it would like for instance, if I did this, table already exists, right? It will not say query okay. All right, and then let's insert something into it. Well, we'll talk about inserting a little bit. All right. So there's this command, SQL command called insert, and that is used to grow vertically. If you look here, insert into persons, last name, first name, address, city values, right? And it's got my info with little black boxes because, yeah. Note that I did not include a person ID. And the reason why I didn't is if you look at the description of person ID, it's an integer. Can it be null? No. Is it a key? Yes, it is a primary. Uh, what is the default? If I don't give it a value, it is null, except for this little extra thing called auto increment. And what auto increment does is if you set a column, as in like if you look at this right here, person ID is an integer, it's a primary key, auto increment. And notice none of these other ones have that, right? Auto increment, what it does is when you insert something, it automatically assigns it a number. And it will normally be one number higher than the one before it. If you do weird things, you could possibly have it not be one extra. For instance, let's say you delete somebody, it might go in there. So don't bank on the fact that it's always one more, but do bank on the fact that it will always be unique. So that one. So notice I did not put a person uh, when I insert or person ID when I insert this data, right? I'm inserting last name, I'm inserting first name, address, city. So let's look at our database over here. So insert into persons. And we just describe, wait, do a show table. Show table. Oh, describe persons. There we go. All right. Which I already showed that, but all right. Insert into persons last name, first name, address, and city. And then I tell it what the values for those things are going to be. So in this case, uh, so last name, first name. Oops, I messed that up, didn't I? Well, oh, hold on. Good, got that SQL error there. There we go. Values. B. Ryan. 1, 2, 3. What did I do? You have an error in your SQL. Oh, misspelled values. There we go. So we've inserted one row into that table. And if I wanted to verify that, which we'll talk about select statements in a second, but boom. You see that there is now a row there. Boom. All right. We can also update. So if I wanted, for instance, let's say I messed up the address, update person set address equal to boom. And now if we select star from persons, what do we get? See, it updated it. Boom. Done. Okay. So we can insert and we can update data. Okay. And then we have the select statement, which is how you get data out. So the easiest is, of course, select star. Select star basically says, give me all the fields. Select star from persons where city equals Linden. Right? Pretty easy, right? Let's throw another person in here. All right, we got Frank J. All right, so select star from persons where city equals Linden, and then select star from persons, right? So you see right here, we have two people, but if I do select star from persons where city equals Linden, magically, I only get one person. So your database is taking care of all of the sorting and things like that, like going through the data for you. Okay. You can, instead of star, you can also specify which things you want, right? So let's say I don't really care about person ID. All I care about is first name, last name from persons where last name equals J. All right, so we got first name, last name from persons where last name equals J. Relatively simple. All right, I gotta pet this cat. It won't go away if I don't pet it. You can also do order bys, like select from persons order by last name ascending. Okay, last name descending. And it sorted alphabetically. Ascending, F is before R, descending, R is after F. Easy peasy. Again, your programmer isn't writing this, you're not writing this. Databases just come with this logic built in so that you don't have to write all this stuff. All right. And then, yeah, person ID is one, even though we did not set it because of auto increment. We know that. Okay. So let's talk more about SQL. My cats are fighting. It's pretty cute. Let's talk about SQL with relations, right? So we did something to get stuff out of a single table, but what I was talking about is relational databases where they link to each other. So I'm going to create another table here, right? So up here is, let's see, so query, okay, so we have another table with orders. We're going to insert something into that. All right, and then we entered an order, so insert into orders, order date, person ID, part number. And as I was saying, like cost, I probably should have been in this. When I was thinking about this, I didn't think about costs, right? A very anti-capitalist way to look at things. So order date, person ID, part number. And so this order date is a date time. If we describe orders, so this is an integer, this is an integer, and this is an integer. This is a date time. And there's a special function in SQL, all of the versions of it, that if you have a field that is a date time and you tell it to insert now into it, what does it do? Well, I mean, doesn't take much to figure it out. It puts now. In this case, it puts it in UTC. You can, as part of SQL, you can tell it what time zone you want it returned in. One crazy thing, and it's not in the slides, about databases and date times in databases is that all the code for handling time zones and things like that, it's all built in. So if you have a customer in France who puts in an order and you have a customer in uh, Hawaii who puts it in order, obviously the time zones are totally different. You can insert into your table their time zone when they made their order, and your database software knows all the offsets and things. And if you then say, hey, give me the orders based on when they were ordered, it will do the time zone math of all those different time zones and give you when the orders were actually made in whatever time zone you want to look at it. It's the presentation of the data should be in your time zone. So anyways, lots of stuff there. Sorry. Anyways, so we have select with relations. And then you're able to join the data. It's called a join when you take data in one table and correlate it with another, right? Customer number, the person in the persons table, that is person ID number one. They might link to the orders table. Well, they do link right there, right? So when you join things, and it gets more and more complicated as you go in. Like for instance, let's go back a little bit here. What if, let's say I'm a salesperson, right? I'm the salesperson and I want to know my commission. Well, I know this, hopefully, probably not. Let's start here. Let's say join, give me my employee number based on my name, join it to the customers database. I don't care about any of the customers. What I care about is then these orders, right? So, link over to my customers orders and then give me the price each on each of them. So I'm joining from here to here to here to here because I want to know how much money my customers have spent this year. Right? So one join, two join, three join, right? And maybe even four join. What if I wanted to know uh I would say like how many laptops they ordered or something, right? All of a sudden I'm linking over here. Maybe I have to join even further because I just want to know, like, okay, I have different product lines. Maybe one is laptops and one is monitors or whatever, and I just want to know laptops. All of a sudden I'm joining from knowing my name all the way over to getting the sales rep employee number of myself to link over to the orders to get all the orders that were made by my customers. And then I'm linking over to see how many of a certain product line they have done. So at that point, I'm joining from here to here to here, right? It's a lot. It's a lot of joins. So SQL can go from being very easy to very hard. But if we look down here, select star from person's orders, where person's last name is V, and the orders dot person ID equals the person's dot person's ID. There's other ways to write that, but this is the one that I always feel like makes sense. If we look at the schema, describe orders, describe persons, right? If we look at the schema, we have person ID here and we have person ID here. And what I'm interested in is orders that are made by person ID 1, but I don't know their person ID. I know their last name though. So I'm like, give me, let's see, select star from persons where persons dot last name equals V. All right, so we have that, right? Then we get the person ID and we see select star from orders where person ID equals 1. So you could do it that way, right? You could first select this and then select that. Or we do a join, which basically just says, hey, I'm interested in, excuse me, people of the last name of V, and show me all the orders where the person ID for anyone whose last name of V is in the orders table. So it's joining the two together. And it takes a little while to sort of understand it. And also there's other ways to write it. I'm not going to try it off the top of my head though. I should have put it in my text file. I would say it would probably be select star from orders join on person ID. Yeah, not even close. You have an error. No biggie. All right, but generally that is the gist. So talk about security a little bit. So databases, they have users, um, and those users are able to query data. You can change they have access controls. For instance, it's very common to have two database, like major database users. Let's say it's like a program, right? You're writing a program. So you create two database users. One of them might be called user read only, and the other might be called user read write. And the way you write your program is, unless you know you're having to write to the database, you always use the read only user. That way, no matter what weird security thing happens or like code injection happens, the user that you're using to log into the database, it doesn't have access to write to it. And then when you're doing write operations, you switch to that user and use that one instead, right? Programs are supposed to do that. Some of them do, some of them don't, but they're supposed to, right? Right, users may only be able to read certain data and read write other data. Uh, Databases, if we look down here, they do have the ability to do network access control, which is, hey, only let this user log in if they're coming from this IP address or from this computer. That's pretty useful if no one is supposed to log into that database, right? Uh, I wouldn't trust it with all of my guts, right? If I had a database and only a program was supposed to log into it, not people, I would also have a firewall in front of it rather than relying on the database to do its own network access control. That way, it's like more layers of security. A database can have multiple masters and replicas. So for instance, let's say I have we'll use like a Chase, right? Chase.com's credit card database is probably pretty darn giant, right? So in that case, one server isn't going to be enough. So what they do is they set up one server that is like the master server, and then they set up a bunch of replicas of it. And whenever that master server gets updated, it sends that update to all of its replicas, right? If I'm like, hey, update the address for this person, I do that update on the master server, and then the replica servers, it will propagate to them. If I have applications that do a lot of reading, I point them at these replicas. Maybe they're not as up to date as humanly possible, but they're pretty darn close. It's also common to have a master database and a replica in an area, and then another replica somewhere else. Again, we'll go back to the Chase.com thing, right? Chase has a headquarter in Columbus. Probably they have a database there. Maybe, who knows? If power goes out, large power outage in Columbus or earthquake happens, they can't just lose that, right? That data has to persist forever. Uh, So they usually ship, you know, they have a replica that's just somewhere else, Chicago. And every time someone updates this database, it also sends the update to the replica that's in Chicago. That way, if something happens in Ohio, it's also in Chicago. And what they would do if there was a disaster in Ohio is they would basically take that replica and promote it to be the master of all the databases, and then your program at that point, you would point it at that database instead. There's ways to do it so that it's not time consuming. Beyond that, databases are routinely backed up and data is shipped offsite. So very commonly, it used to be 20 years ago, e-commerce sites would like take a couple hours in the weekend and shut down their database, do a backup of it, bring the database back up. The reason being, what happens if you take a backup while the data is updating? Do you get all of it? Did you not? So they used to shut it down, back it up, bring it up. These days, not so much. There's commands that are good enough to sort of what's called QS the data, make sure it's not actively being updated at that very second. Then they grab it. In database, there's this concept of locks where it's like, hey, I'm updating this right now, so therefore no one else can update it. And so maybe you're locking a column or a row. And like, let's say for instance, I need to update this address. The database software would automatically lock this column, or excuse me, this row, so that nothing else could update it. It would make the update and then it would unlock it. That keeps your data from becoming corrupted. And then let's say there was two updates. The other one would wait until the first one completed. It would wait until it was unlocked and then it would do its thing. You can run into problems in databases where someone goes to make a lot of changes all at once, usually using pretty complex but poorly written SQL. If you give a database server very basic SQL, it will do things very quickly. It will look at what it needs to do. It will analyze it and say, okay, I need to lock this. I need to do this. I need to do that. If you start sort of giving it very specific instructions, it might like, oh, please lock this one first. You might get sort of caught into a problem where, for instance, like what's called deadlocking, where like, hey, uh, don't update this customer number until you update the street address, but also this street address is locked until someone updates this customer number, and you're like, oh no. Those things can happen if, but you gotta start getting good at databases before it actually happens. So you don't have to worry too much about locking. All right, terms for the future. So these are some terms that we routinely use with database. ETL is huge. Extract, transform, load. Any sort of job that takes data in whatever format, takes stuff out of it and then inserts it into a database, that's an ETL job. Um, fill out the Scantron, put it through this computer. The computer pulls the data out of it, and it's like, okay, insert into this, insert into here, insert into there, into this, right? Things have gotten even more complicated. There's OCR, which is the ability for computers to read, handwritten text. That's a thing. It's all part of this whole ETL thing. Let's take data, transform it, maybe try and sanitize it as best as possible, and then put it into a database. Okay. A data warehouse. So a lot of times in the world of databases, you have data that you might not necessarily be interested in any of it specifically, but either for regulatory or for like trend ideas, you need to store all of it. And that's a data warehouse. It's where someone would store a ton of structured data. Now, there's so much data that getting the data is very slow. But most of the time, a data warehouse you're not trying to get the data very often. You're writing data constantly. You might necessarily not be interested in how long it will take you to retrieve the data, but at some point you do have to go retrieve that data. It will be slow, and everyone who runs a data warehouse sort of understands that. So there's also a data lake. So data lake is a sort of a new term within the last, we'll say, 10 years. And so if we look at extract, transform, load, right? I'm taking data from one format, parsing it, and then putting it into a database. A data lake never does the actual, well, it does the putting into a database, but it does it very weirdly, right? So basically, I take all the stuff that normally I would put to an ETL job and I just store it. And then as soon as I need anything from it, my database program, or in this case, data lake program, does the ETL job all in this huge batch all at once, gives you the data back, and then destroys what it just created, and you're back to this lake format, right? So it's in this native format. Computers are now so fast that they're not as concerned as getting not as concerned at getting things into the database. Uh, they know they can just create the database on the fly, get the data, drop database, keep the lake. So you're not doing these little tiny ETL jobs every time new data comes in. Instead, you're just doing one giant ETL job uh, every time you do a query. Amazon's real good at this. Google has one. I think Microsoft has a data lake that I think it's actually called just data lake because why not, right? Um, it it's pretty interesting now that like because of the fact that we're creating so much data, um, we can't keep up with creating all these ETL jobs or whatever. So now that computers are so fast that you can just have the ETL job done in a big batch real quick right off the bat. That's pretty cool. Storage compute trade-off. So if you don't want to compute, you store. If you don't want to store, you compute. Um, Basically, I like to use multiplication tables by this. So when you're a kid, you learn these tables, right? 3 times 3 is 9. And usually you can get up to like, double digits, 10s, 11s, 12s. But there's a point at which your brain just can't do it, right? Like my brain can do uh, 10 times 10 is 100. I have that memorized. My brain can't do 11 by 11. I mean, it might be able to, but we'll say it can't. Um, at that point, I have to compute it. So either I'm memorizing something or I'm computing it on the fly. Memorizing something is always faster, but it uses up space in my brain. Uh, some of these things don't happen often enough that I should memorize them, so I compute them. And that is the concept of storage compute trade offs. Sometimes it's better to compute, sometimes it's better to store. Um, if you go back years and years and years, hackers would basically take every word in the dictionary and encrypt the word, check to see if that encrypted word matches the encrypted password they stole. If it didn't, they go to the next one, the next one, the next one, the next one. They keep computing, comparing. Because the fact was, like, it took so much room to store all those encrypted passwords that you were trying that computing them on the fly was easier. Go forward 20 years, computing power has doubled tenfold, and so has storage. So at that point, there's just a little, database in the cloud that now has all that stuff in it, and someone just does a, select star from encrypted password database for hackers, where uh, encrypted string equals, and then they give it the string that they stole, and boom, they get the password right back because someone doesn't mind paying for that storage. All right, no SQL. Super fast database that limits the amount of functionality in exchange for speed and scalability. For instance, not all nodes might be not all nodes might be up to date and could return older data, which I sort of went glossed over that with data warehouses and replicas. No SQL if you look at things like Facebook, which has a very large and pretty fast database, right? They use a lot of NoSQL, a lot of key value types. So big data is a part of this. The science of processing large amounts of data with data warehouses, data lakes, key value databases, and various ETL tools. the concept of just taking a data lake, doing a giant ETL job, and being able to query it, that is big data. Um, we have so much data right now that, for the most part, we are waiting for compute to catch up so that we can process all the data we've been holding for the last 20 years, right? Uh, but if you look at, for instance, Netflix, you go into Netflix and it's like, here's some stuff we recommend for you. And then all of a sudden you're like, yeah, but I'm going to start searching for this. It's doing SQL calls in the background to their big data databases. Like, you start searching, you're like, I'm looking for a movie that starts with M, and there's a query that just kicks off that's like, selects star from movies where name begins with M, and then you type a O, and it executes another query. Select star from movies where name begins with MO, and it keeps doing that. And you see it on your TV as you're typing, it's giving you different results back. That's what big data has been able to accomplish for us, is like, it's so easy to get data back in almost real time that people think they're interacting in real time when actually in the background there's just these giant databases of big data. So, all right, if there's any questions, throw them in the chat. If there's not, I will give it a couple minutes. We'll see. Oh, I should. There we go. I'll just keep petting this cat. It's getting a little dark out, so. Uh, did it? Okay, so the question is, did it take a long time for you to learn this stuff? Uh, well, it's taken 25 years. I will say it did not take me long to get started. And then from there, it just becomes, um, the quest, the forever quest for knowledge. So I started when I was like 16 or so because I just was interested in computers. And so I was just like, I don't know, what I'll go learn Unix. And then it was, then I got a job, and then they were like, we need you to look at this database. So then you just have to pick it up. The beauty is that everything is in Google. People always joke. The best way to recommend to get started into IT, that one I do know how to answer. Figure out the thing you want to do in IT, and then just go do it. So, for instance, if you want to be a systems administrator, go to the cloud and get a system. Uh, Google Cloud, Amazon, they all give them away. If you want to be a database administrator, the best thing to do is, go to the cloud, get yourself a database. They make tiny, it used to be like a big process of like setting up environments and things, getting computers, doing things. But now with everything in the cloud, if there's something you want to do, mostly the what's holding you back is you, as far as there's usually a $20 Udemy class that you could take. I freaking love Udemy. I don't know why anyone goes to college. And then you just do it. And then you just put it on your resume, right? I would say if you want to be a programmer, go into GitHub and look for the projects that you use, right? There's always open source stuff out there that you are probably using, and just join the development team. There's always on GitHub, uh, there's always issues, and what issues are bugs. Like, someone's like, oh, I tried to install this on Ubuntu 17.2 and I got this error message. Just go in there and be like, okay, I'll try and fix that issue. All of a sudden, you're a programmer. You didn't think you were, but all you have to do is say, like, oh, I'm going to do this thing, and then try to do the thing. You don't even have to succeed. trying to do the thing is usually enough to teach you, like get you far enough ahead that you could possibly make that into a career. Because there's just not enough programmers, database administrators, system administrators, security people. There just isn't enough out of them. So anyone who shows interest, and especially enough interest to take a Udemy class or go onto GitHub and contribute some code, or someone who like learned enough SQL, like brought up a database, people will hire you because 99% of the population doesn't know those skills or doesn't have the inkling to start those skills. So really, most of these places are just looking for the people who are interested, not necessarily interested, and then at least put in the time to start learning it themselves. There is definitely, and there's a million of these resumes floating out there where people are like, "Oh, yeah, but I'm a good learner. I You should hire me. I'll be a really good programmer. You just have to teach me." And it's like, okay, but this guy's also smart and he took the Udemy class already. So which one do I hire? I hire the guy or girl or non-binary who took the class in advance because I know that first of all, they at least know enough about it that they're going to try to make this a career, right? There's plenty of people who are like, "Oh, I'm going to be a programmer." They get a job and then they're like, "Oh, I hate programming." And it's like, well, I wish you had told me that before I hired you. Yeah, Udemy, Udemy. It's a marketplace of classes and a lot of IT stuff, a lot of other stuff on there. But instead of like, no offense to college because it's definitely a thing for certain professions. Uh, I would much rather pay $20 for a guy who's like putting classes up on the internet than I would for uh, going to college. College is great if you need like coaching or a TA or something, but if you're self-taught, if you're have the ability to teach yourself things, um, you can just start. You can just do it, and it'll be hard, right? But there's Google. So the funny thing is, you're like, oh man. So on Udemy, I'll talk more about Udemy, right? Let's say you take the. I recently took, I think it was Ansible. It was a class on Ansible, and they had me set up these virtual environments and things, like pretty complex stuff. It wasn't working. And I was like, man, this thing isn't working. There's like a Q&A on every class. So what you can do is go look at who's asked, and of course someone was like, "Yeah, I couldn't get this to work on a MacBook," and I was like, "I'm also on a MacBook," and then so I was like, "Why doesn't it work?" So then of course I go into Google and I'm like, "Why doesn't virtualization work on this?" And I was like, "Oh, it doesn't work because I'm on Wi-Fi and this version of VirtualBox sucks at Wi-Fi." So I had to go search out my answer and I learned something different. But then I went back in the Q&A section and wrote like, "Hey, just so you know, I ran into this problem. I found out this is because of this, and this is how I solved it." So that the person ahead of me or behind me has the answers to the problems that they might also run into. So Udemy has people's questions, people's answers. They're rated by how helpful they were. So if someone's just like, if someone takes a class and every student runs into the same problem, that question is going to be very high up on that course, or that section of that course. Yeah, and that's it. So you Udemy is definitely a good place to start for taking classes. You just have to tell yourself, okay, I need to start taking these classes. And then once you do, like it's just gonna be hard. It's gonna be hard whether you're in college or whatever, right? It doesn't matter. It's a hard thing. It's not the hardest thing you're gonna do, but it is gonna be time consuming because you're going to have to search for answers. And that will never stop, right? To this day, I still have to Google things. It's not like I know, you know, 25 years in, it's not like I still remember the stuff I learned 25 years ago. Uh, sometimes I'm like, oh, what's the syntax for this command? Or what was the name of that weird, like, security vulnerability? Things like that. Yeah. So I'm going to call it. I appreciate the questions. I will come up with a topic for the next one. It will be in about a month. Let me see. Gotta look at my calendar. Hold on. Yeah, second Thursday of every month. So it will be on September 8th. I don't know what I'm going to do yet. I have some ideas though. If you think of something though, let me know. I have some ideas. Productivity is a good one. Uh, cybersecurity is a good one, like cybersecurity basics. Maybe cybersecurity. Yeah, I think cybersecurity will be next month. So that'll be a good one. And I think that's about it. Cheers to everybody. Have a good night. I'll put this up on YouTube within the next day or so and post the link. Have a nice day.